contrast, at least in some cases of MODY X, probably we have a primary genetic defect of the beta cell that is not as severe. Therefore, if this is not challenged by other alterations like a deficit of insulin sensitivity, this will not really result in high blood glucose. But if instead you put other genes or other environment, the clustering families, then you may have a rise in high glucose. So this then becomes really interesting because it's really resembling what we see in type 2 diabetes. So I would argue that some of these families may serve as a model to reproduce in a simplified way, if you will, what we observed in the common forms of type 2 diabetes. Therefore, dissecting the genetic architecture of diabetes in these families can give us some really precious insights in the etiology and perhaps even in the management of common forms of type 2 diabetes. So we get then to the second questions. How can we identify these other additional MODY genes? Now, a disclaimer, I'm using the terms MODY just because it's simple to use, but I think that MODY perhaps is another box as type 1 and type 2, and I think that with time we will actually move forward and we'll abandon that kind of box and we'll call the forms of diabetes with a more precise classification based probably on the mutation of the gene that is at play. But anyway, candidate gene studies, of course, is one of the methods that has been employed. And this is based on studying genes that are known for one reason or another, are postulated to play a role in beta cell physiology. And this has been fairly fruitful. And after MODY 6, which was actually the form that, perhaps I actually included MODY 6 here, which Maciek, as many of you will know, I guess, was the discoverer. So we had MODY 6, then we have MODY 7, which is identified in France, and it's a transcription factor, KLF11. Then MODY 8, which is the form with the exocrine insufficiency described from the group in Norway, from Paul Njolstad. Then we have PAX4, which was some mutations were identified in families from Thailand. And then more recently, we also have some mutation in the insulin gene. Then although they give rise more commonly to neonatal diabetes, they also in some cases have been identified as a cause of MODY. So this actually is what you find in OMIM. So just to answer Maciek, it's true that perhaps in the official classification they do not appear, but if you go to MODY you will find this kind of numbering. The other approach is that of positional cloning. Basically you screen the entire genome for regions that co-segregate with diabetes in the family, then you go into that region, do sequencing, and try to identify what is the causal mutations responsible for that segregation. And this is, of course, the approach that was used for HNF1 alpha and that for MODY 3 and led to the identification of HNF1 alpha. And using this approach, we were able to identify what OMIM calls a MODY 11. I don't know whether it's a MODY gene or not. Again, I would stay perhaps away from those classification. But anyway, a gene that seems to play a role in autosomal dominant forms of diabetes with an early onset. And this gene is BLK. And in the next few slides, I would like to guide you, to walk you through all the series of experiments and studies that we did, my group did, to identify this gene BLK as a gene contributing to these forms of diabetes. So back in the early 2000s, we have done a genome-wide screen using 400 polymorphic markers, and we had identified some regions of linkage, and upon further refinement of the linkage, we found some convincing evidence on chromosome 8p23. You see there was a log score of 3.66, barely there, but nonetheless sufficient to trigger a positional cloning effort. And the important thing to remember is that this 3.66 actually was coming from a bunch, only from a small number of families. And so that was significant evidence of heterogeneity. There were only 5 families which had a positive log score, say, before 0.75. And so we had also a significant H-LOD, heterogeneity LOD score. And, but this is important because the positional cloning approach assumes that you have enough families to see a peak. If we had only 1 or 2 families, probably we will not be able to see much because the positive signals will be overwhelmed by the negative families. So this is actually a challenge for the future. As less and less families are due to a single gene, it will be more and more difficult to find them through this approach. So by doing some positional, finer mapping, and this was done by a fellow from Łódź, Maciek Borowiec, he is here in the audience. Here there is Maciek. And we were able to narrow the interval to 2 million bases. And basically there were 15 genes, known genes, 20 genes derived from ESTs. And Maciek, with a lot of patients, resequenced all the exons, and at least 2 kb of 5' and 3' flanking regions, and also many conserved intronic elements, a total of 732 kb. This was before next-generation sequencing. This all was done manually using an ABI sequencer, so it was a lot of work. So we found 410 sequence differences, and of these 410, we found 5 that were segregating with diabetes, on the haplotype that we had found linked in the linkage study, and had a frequency in the population that was below 1%. And of these 5 mutations, 3 occurred in the same family as a haplotype. 1 mutation was a non-synonymous, changing amino acid from enala to a threonine. 1 was in the 3' UTR, and 1 was in a conserved element in the 3' flanking region of the gene. The other 2 mutations occurred uniquely in the other 2 families, and 1 was right after the polyadenylation signal in some conserved element there as well, and the other one was instead on the 5' flanking region of this gene BLK. So here is the segregation in the 3 families in which we found these mutations. We had 25 mutation carriers. Of these 25, 21 were affected. So we had a less than 100% penetrance. One of the known penetrant was an individual still 10 years old, so they still become at risk of diabetes, of developing diabetes later in life. But 3 of them belong to this large family where there was a very good segregation with diabetes, with exception of these 3 individuals where we had incomplete penetrance despite a fairly advanced age. And the characteristic which was interesting of this individual is that they were leaner, significantly leaner than the rest of the family, than the affected. And the LOD score of these families was 1.2, in this family 1.6 and 1.0, but when you accounted for in the linkage model for a BMI-dependent penetrance, actually this, although this was a kind of ad hoc, post-hoc analysis, this LOD score increased to 1.9. And you can see the issue of BMI coming up fairly clearly in this table comparing the clinical characteristics. And you can see that individuals with the BLK mutations, they have a BMI of 28.7 as compared to 24.6. So we go back to the issue of the need for something else in these families in addition to a insulin secretion deficit. And you can see this well when you look at the serum insulin during OGTT, and you see that it's markedly elevated, but these people are really hyperglycemic, so even though elevated, this insulin is not sufficient to produce the appropriate stimulus, so that we are in a situation of relative insulin deficiency. So we were still a bit hesitant about to believe what we were seeing, because this was somehow the first example of such form of autosomal dominant diabetes with this kind of features. So we tried to see whether we could get some clues from the gene that seems to be affected. And the gene is BLK. It's called BLK because initially it was described in B lymphocytes. And it's a non-receptor tyrosine kinase of the SRC family of a proto-oncogene. And it's involved in the transduction of some signal, although it's not really clear which signal this is. But we know that it's involved in cellular proliferation and probably in cytoskeletal organization and cell-cell contact. And again, it had been reported to be expressed only in B lymphocytes, where it mediates activation signals. Well, the first thing that we had access to Affymetrix data, expression data in islets, and we saw that even though the gene had been found to be expressed only in B lymphocytes, actually we saw signal in islets with both probes on the array. And also was kind of interesting that we're seeing a slightly higher signal in a preparation where the RNA had been enriched in beta cell by laser microdissection. And we confirmed the expression of this gene in islets by RT-PCR and also by immunofluorescence. You can see that, well, perhaps the light is not the best, but of course we see that in spleen and tonsils because it's expressed in B lymphocytes, but also you can see in the islets, in the pancreas, and also in the hair follicle, Leydig cell, in the salivary gland. And of course, importantly, in the islets, there was a colocalization of BLK and insulin suggesting that this was expressed in a fairly specific way in the islets in beta cells. So we wanted